will be okay for the recording. Okay. So regarding this one thing about this, the quiz that we just took last week. So let's open the, oh no, I don't know what happened. I think, let me check. Okay, so this is the result of quiz 2. So actually more than 45% got full mark. And then there are 2% who actually got 0. Okay, this is quite alarming. Okay, and then the rest, I think most of you are probably here. Okay, which should be fine. So this is 5%. So the marks that you get actually is the real mark for your final exam. I mean, for your final mark. Okay, so you should be able to see your marks, your answer, and the correct answer in UKM Folio, and then please check them. Okay, so as I said, so next week, okay, we'll have another quiz. Okay, week 13. Sorry, week 14. Okay, we have another quiz. Quiz 3. Okay, so the format is the same. Okay, the topics. Okay, I think polar coordinates. And then what else? Surface area. And then the topic that we learned last week. Yeah. So triple integration or triple integral in rectangular coordinate. Okay. So this is 2-dimension. This 2-dimension or double integral, and the last one is triple integral. This is double integral, this is double integral, and this is triple integral. Okay, so okay, I think that should be fine. And then, yep. So let's go to the topic. Okay, so last week we just had a look at a few slides. So let's just start from the first slide. Okay, so these are the topics. Okay, introduction. Okay, so sorry. Oh, okay. Oh. Okay, good. Okay, so like what you had for double integration, I mean for triple integration in rectangular coordinate. So in this cylindrical coordinate, you have this what do you call it, box or solid. Okay, but the solid is not it's not rectangular box or rectangular solid. Okay, so there are 3 quantities. Okay, there are 3 quantities for this box, or what you call it as cylindrical wedge. Okay, so these quantities actually 2 for the r, okay, which is the distance, okay, from the origin to your solid. I mean, actually the inner boundary and outer boundary of your solid. And then there are 2 vertical half planes, which is the left and right boundaries of your solid, and then 2 horizontal planes, actually the z, I mean the the bottom and the top part of your wedge. Okay, so for Cartesian coordinate, usually you have something like, let's say, G, which is X, Y, Z, where X from E to B, and then Y, for example, from C to D, and then Z, okay, probably from E to F, for example. Okay, so this is, I mean, all these three components actually, I mean, you still have three components for for cylindrical coordinate. So this is Cartesian, okay, but for cylindrical coordinate, you still have three components, okay, but as I said before, is R, and then theta and Z, okay, and then this is what we are going to discuss today. And this Z is actually the same Z. Okay, if you have Z in your Cartesian coordinate or rectangular coordinate, then that same Z value or Z function or function of Z can be used for the cylindrical coordinate. Okay, so the difference is that you have X and Y in Cartesian or rectangular coordinate, but now you have R and theta in cylindrical coordinate. But they are actually known. I mean, you've seen them before, okay, from the polar coordinate, okay, where X equal to R cos theta, Y equals to R sine theta, and solving this, you get X squared plus Y squared equals to R squared. Okay, so in short, okay, cylindrical coordinate is actually polar coordinate. Cylindrical is 3D, polar is 2D. So polar coordinate plus Z component, okay, or yep, this or Z. Okay, so polar plus the Z component, I think this is what the component here, and you get the cylindrical coordinate. So this is polar 2D, Z component is just 1D, and you get the 3D. Okay, so sorry. Okay, so you have here the blue color, the blue wall here is actually the inner boundary, and okay, because I mean from here you get this, and then another one which is the outer boundary of this wedge or cylindrical wedge. Okay, so this is actually comes from a circle with radius r1. Okay, and the outer boundary comes from the circle with radius r2. Okay, so but you just take the small portion of the circle to get the inner boundary and outer boundary. Okay, and then the second one is the yellow color. Okay, which is this one, and I mean the other side you get another one. Okay, this actually the vertical half plane. Why is half plane? Because okay, if I mean for polar coordinate, let's say you have something like this. So let's say this is your x. I mean your polar axis is theta equal to 0, and then this is your y, which is theta equals to pi over 2. I mean, in general, they usually take your x as theta equals to 0, but it can be actually different. I mean, you can take your theta equals to 0 from here, I mean from y, it doesn't matter. Okay, but I mean in general, usually the x-axis is where we start counting, or we start the counting the theta. Okay, so if I ask you what is the I mean draw a line, okay, with the angle theta equals to pi over 4 radian, I mean, which is 45 degree, then this line, I mean the line for this would be something like this. Okay, so the angle here is pi over 4. Okay, so the line must start from here, from the origin, and it can be extended. I mean, it can extend until infinity, but in this direction. Okay, so it's like, so what you call it is a half line. Why can't you extend this to, for example, to here? I mean, in the opposite direction. Okay, why? Because this line has different angle. Okay, so this line here, the angle is, and so it's different, and so I need to use different color. I think this one. Okay. Oh, sorry, just forgot the ruler. Okay, so this is, what is it? Pi over 4 plus pi over 2. And okay, which is 3 pi over 4. Okay, correct me if I'm wrong. Okay, so that's why your line starts from the origin, or the pole, and you call it pole in polar coordinate. Start from here and extend until the positive direction. So which means that here cannot be included in your line. Okay, so that's why it's just half line. I mean, like, it's half of the axis. I mean, it just goes to the positive direction. In this case, I mean, similar here. When you try to in 3 dimension, yeah, when we say theta equals to certain value, for example, theta 1, okay, so we call it half plane. Okay, because the plane start from the z-axis. I mean, start from here, start from the origin. Okay, so let me take this. Okay, so you have this. Okay, so theta equals to 1. Let's say, sorry, let's say you want to draw a plane where theta equals to theta 1. So let's say this is the angle. Oh, sorry, it's ruler. Let's say this is the angle where theta equals to theta 1, which is actually this one. Okay, so you can draw multiple lines. Okay, it doesn't matter. For any value of z, theta always equals to theta 1, because in this equation, I mean, in this very simple equation, there's no z. Z is not in the equation, which means that regardless of the value of z, theta will always be equal to theta 1, which means that you can have multiple lines. Here, not only this, but you can draw more of this, like this. Okay, but not only that, This is also true when theta is, let me extend this z-axis. Okay, so this is also true when z is negative. I mean, like you just don't care if z is positive or negative. Okay, so taking all this together, you get a plane. I mean, a half plane. Okay, you call it half plane because it starts from the z-axis. Okay, so this is half plane, and because it starts from z-axis. Okay, you can't extend. I mean, if you extend this, I mean, if you are able to extend this to this, I mean, to infinity, then it's called a plane, a full plane. But the angle is different in this case. Okay, I mean, it's like this. If you take the other part here, then the angle is not pi over 4. It's actually 3 pi over 4. That's why you don't include this part. So it's the same as this. You just take this half. You don't take the other half here, so just cancel them. Okay, this one is called half plane. Okay, so here you have two vertical half plane. Why two? Because first is for theta 1 and the other is for theta 2. And then you have two horizontal plane. Okay, this is full plane. I mean, like it can extend to whatever value of x and y. So in this case, you have one, which is a small part here, the wall, sorry, the floor, or the bottom boundary, or the bottom surface of this wedge, and the other one is this one, the top boundary of the surface. Okay, so the dimension of this is, just the width, the ketebalan, and the thickness. Okay, in all direction. I mean, like delta theta is actually the angle between here, which is theta 2 minus theta 1. Delta r is actually the distance, the difference in distance between these inner and outer boundaries. And delta z is actually the difference, the thickness, or sorry, the height, or the difference between heights, or the difference in heights between the bottom boundary and the top boundary. This is quite obvious here. I don't need to describe this more. And this actually delta theta, delta r, delta z is called central angle, thickness, and height of the wedge. Okay. So let's go to the next. Okay, so what is meant? We've seen this before. What is meant by r equals to 1 in 2D? So in 2D you get a circle, right? But in 3D you get a cylinder with this equation, because r equals to 1 equals to, always equals to x squared plus y squared square root 1, which means is actually a circle in 2D, but in 3D it's actually the same equation, but it's a cylinder. Yeah, we discussed this before, so I need to explain this more. And then theta equals to pi over 4, as I said just now. Theta equals to pi over 4. In 2 dimensions, we have a line, half line, or a line, but it starts from the polar axis, or the pole. Sorry, a line starts from the pole, and the angle is measured from the polar axis, or the x-axis. And then for the 3D is actually a half plane, as I draw here. And then z equals to 2 is just horizontal plane. Okay, horizontal plane with angle, sorry, with value 2. in the Z axis. Okay, so is there any question? I'm sorry because I can't see you, so I'm not sure whether everything's okay or not. Okay, if you have question, just you can ask, or if you don't have a mind, so just type it in the meeting chat. Okay. So let's go to the next slide. Okay. So it's what we've seen before when we want to define triple integration or double integration. In fact, okay, we discretize or we divide our domain or our region or now our solid into smaller parts. Okay, like this. So let's say you have a wedge here, and you divide them into smaller parts. Okay, assume that this G can perfectly be divided into certain sub-region or sub-solid, and you get something like this. Okay, assume that you have n such smaller cylindrical wedges, like this, where the volume for each here is delta Vk. And then you take an arbitrary point, okay, from each small sub-region, sub-solid here, or small wedge here. Okay, so you denote it as something like this. So you have three components, r, theta, and z. Yk, y is k here because it's the kth wedge. Okay, and then star, which means that it's an arbitrary point. You can take point here, you can take point from here, or from the mid position of the wedge, or any position as long as it's within the wedge. Okay, and then you can, of course, you can calculate the product between the volume, which is here, there's the Vk, times certain value of function. Let's say you have a function f, where f is a function of three variables. There are r, theta, and z in f. Okay, and then this f, let's say f is defined. You have this point here. You want to know, the value of the function f at this point is this point. And then you multiply it, you get something like this. And then you repeat this process for all n small wedges here. You have this n numbers of small wedges, and you just calculate this for each wedge, which means that now you have k start from 1 until n. Okay, you multiply and you add, you find the, you just add them, so which means that you get the Riemann sum, something like this. This actually similar to this, except that now you have the summation. Okay, and then if you keep repeating this process, multiply and add, and then take the limit, which is the limit of the number of the small wedge to positive infinity, and then this actually can give you the triple integral here of f. Here, this is here and here, and then you have the delta v, which becomes dv. Okay, so this is only true if the limit exists. Okay, so it can be shown actually that hang on. Okay, let me see. Delta A. Let me see. Okay, it can be shown actually the base of each subbox. Sorry, not subbox. The base of each wedge. I mean the small wedge is something like this. I mean like delta A equals to R times delta R times delta theta. Okay. So if this is the area of the base, then the volume. So the volume here is actually the product of the base times the height. Okay, and you know the height is delta Z. I mean, like, of course, I mean, just recap. So let's say you have a rectangular box like this. Okay, so this is, I mean, the base, and this is the height. Okay, let's say the height is delta H, and the base is delta A, which is actually equals to here delta X, delta Y. Oh, sorry. So the volume, which is delta V, is equal to delta A, which is the area of the base, times the height. So you get delta X, delta Y, delta H, or you can use delta Z if you want. But the idea is to find the volume of certain solid. You just multiply the base area with the height or the thickness or whatever you want to call it. So the idea is the same. Here you have delta V. I mean, just ignore the K and the star here or the asterisk here. So delta V is actually equal to let's just take this here. Okay, and this is actually delta E here, okay, which is the base area of the case wedge or small wedge. Okay, and then this is the height of the case wedge. Okay, so you just multiply them, and you get on this. To substitute this, the one that we just discussed here, into our equation here. I mean, just plug in here, so you get, now you updated your equation from 1 to here, which is now, rather than delta, you have delta bk, so it now becomes something like this. Okay, and then this formulation, or this formula actually, suggests that a triple integral in cylindrical coordinate can be evaluated as iterated integral of the form something like this. I mean, you just maintain the f, you don't change anything. Now rk becomes r, delta r become delta r here, delta theta is delta theta, sorry, delta theta, d theta here, sorry, and delta z is dz. I mean, it doesn't matter, right? About the order of the integration, okay, as long as you have appropriate limits. But the important thing is that you have all the components in here. I mean, all the components here must be in your formula for the integral. Okay, you have everything now. I mean, the f, the r, the delta r, which is dr, delta theta is d theta, and delta z is d z. Okay, note that from 3 here, okay, as you can see here, integration with respect to z is done first, and you integrate with respect to z followed by r and theta. But of course, I mean, as what we've seen before, we can actually change the order of integration, okay, as long as appropriate limit is given in your, to your integral. Okay. Okay, so we've seen this before. I mean, like when we have a solid, okay, and then our solid is G. Let's say we can find its projection on the certain plane, let's say the XY plane, okay, which means here the projection of G is R. Then the integration here, or this formula, any of this formula actually can be reduced, or can be reduced, not really reduced actually, it can be rewritten as the 2+1 integration, which means that now you have double integration to integrate or to do integration of f over g. Now your integration is that you integrate first with respect to z, and followed by the double integration on over r. Okay, so it's quite, I hope you can see the difference between them. This is the formula here. There is no r mentioned in it. Okay, but here you decompose this g into r is here, and the z component. Okay, so the advantages of this, one of the advantages of this is that you can solve this with respect to z first, followed by using any of the polar coordinate, Cartesian coordinate, and so on to solve for this double integral. But since this is a cylindrical coordinate, so r will be integration with respect to r and theta. Okay, so you have this, and it's up to you. You can remove this square bracket. So I just remove it. So here my integration, I just copy this from here, and then the double integral, here I solve it with respect to theta and r. So here dA, it becomes r dr d theta. Okay, so I just take this and put it here. Oh, sorry. So let me just take everything and put them. Oh, what happened? Okay. Oh no. Okay, good. Okay. So since we are talking about polar coordinate, so here dA becomes r dr d theta, and here it becomes theta from certain value, certain limit to another limit, and this is r from certain value to another value. Okay, and then of course you can combine this with z, okay, and so on. Okay, so this is actually very similar to what we've seen for triple integral in rectangular coordinate. Okay, so determining limits of integration in cylindrical coordinate. Okay, the first one, this is actually similar to what we've seen before. Okay, so we identify the upper surface, which is G2, and the surface that becomes the upper boundary of the G, or of the solid. You need to identify this and the bottom boundary, or the bottom surface. Okay, so if you are able to identify them, then this surface, which is given by G2 and G1, will be your limits for the Z integration. And then you are left with R, and then you just make a sketch, and you can get the R and theta limit like what you did for the polar coordinate. Okay, so let's have a look at one example. Sorry. Use triple integration in cylindrical coordinate to find the volume of the solid G is bounded above the hemisphere and bounded below by the xy plane and bounded laterally from the sides by the cylinder. Okay, so let me see. Okay. Okay, so you have this um, uh, solid G, and then it's bounded by, the roof is actually part of the hemisphere or surface of the hemisphere. And then you have the XY plane, which is Z equals to 0 as the bottom boundary or lower boundary of this G. And then you have the wall of the cylinder, which bounds the solid. Okay, so it is very, very clear, and you've seen this before. Okay, so so you get something like this. Let's take this. Okay, so this is x squared plus y squared. From here, x squared plus y squared equals to 9. You can make it to be r squared equals to 9, which means that r equals to plus minus 3. Okay, since r is the distance from the origin, so you just take the positive value. Okay, and then you have this, which is the equation for the roof, which is represented by the, or produced by the hemisphere. So you have z equals to square root of 35 minus x squared minus y squared, which is this, because x squared plus y squared equals to r. So you got, now you have this. Okay, so here the solid G is bounded below by the xy plane. Why? Because the solid G is bounded laterally by the cylinder. The cylinder can be infinite in any direction. Okay, but here is the cylinder is represented, is bounded by the hemisphere, and the bottom or the base of the cylinder is actually comes from this xy plane. Okay, you need the xy plane, otherwise your cylinder will be unbounded in the direction of, in the negative direction of z. Okay. Okay, so let's try to write. Okay. Yeah, another one. Okay, in this case, you are not given f. What I mean here is that f, r, theta, and z is not given. Let me write it. Okay, it's not given. Okay, so as I said in previous class or previous lecture, if the f, which is a function of 3 variable, is not given, usually you will be asked to find the volume, or probably the surface area, something like this. Okay, but now I'm referring to our question. You are asked to find volume. Okay, so very good. So let's write the formula. Okay, so we have this triple integration or triple integral over g of the function 1. Okay, because when you want to find the volume by using triple integration, then your integrand should be, or will be 1. We have this. Okay, and then you can use this, which means that in order to solve g, you will decompose this g into the base, which is r, and also the height, which is the z components. So now you have double integration over r, and you can write the bigger square bracket here. Here you have z, and this is 1, which means that this is dz. And here, okay, so your z, okay, this is the upper boundary, and this is the bottom boundary. So z will start from 0 until 25 minus r squared, then square root all of them. Okay, so you can write it as dA if you want. Okay, and then so let's expand this and just remove the square bracket. Okay, this is 25 minus r squared 1 dz. Okay, let's say you want to do, I mean, as usual, like probably r dr d theta, which represent dA here. So this will be your r, this will be your theta. Okay, so r is a circle. Okay, so r is a circle. The equation of r is actually the equation of the cylinder. Okay, which means that it's a full circle. So the angle is from 0 to 2 pi. I mean, like if you have something like this, let's say this is your y, this is your x, and then the radius is 3. So you start from this and you finish the whole thing, which means that your angle is from 0 to theta. And you want all points here. I mean, just take. You want all points inside the circle, okay? Which means that your r is from 0 to 3. Any points at the origin until any points at the boundary, that, which is from R0 until R3. Okay, and then you do integration. Okay, something like this. Okay, just check if everything is there. Okay, and then this R here, bring it to the integrand. Get this. Here, as I said before, you have the r squared here, and there's a r here. So you take everything here equals to u. I mean, if there's no r here, just take r. I mean, just manipulate it using trigonometric function, as I said before this. So now you take everything inside the square root to be equal to u, and you substitute, and you get r0 correspond to u equals to 5, and r3 correspond to u equals to 4. And then your theta, I mean, you don't change theta because now you just consider r, not the theta. Okay, since this bottom or the lower limit is greater than the limit here, so you need to switch their position. And just swap, just swap the position, which means that you need to multiply with -1, hence the -1 here now not there. You get this, and this is easy to integrate. You get something like this, and you get this. Okay. Okay, now the question is, can we get the same answer if the integral is expressed in rectangular coordinate? Okay, so how do you do it? Okay, so you have something like this. Okay, so I mean the difference, I mean, for both Cartesian or rectangular and the polar coordinate, I mean, as we discuss here, they both need z, and this z actually is the same as this z. But now, rather than using r theta in cylindrical, how about using xy in or from rectangular coordinate? So this is in polar, sorry, in not polar, in cylindrical coordinate. So in rectangular coordinate, Okay. Hang on. Let me see if I can do this. Or no, actually you just continue. I mean, just take this. Oh no. Okay, it's actually the same thing. But yeah, of course I need to erase this and this. It is actually the same because you're using the same Z, but now it's different. It's different, and this is also different. Okay, so let's do it together. Now you just maintain the Z. You don't change it because they are the same. But let's say you want to do dy dx. So the A now becomes dy dx, which means that now this is supposed to be y and this is x. So we take this and just put them here. And then let's say you draw a line. I don't know what color of the line should I use. Let's say this. Okay, you start from here. I mean the points here, and you move it to the positive x direction, and you get something like this until when you reach x equal to 3. And then the boundary here is actually the upper semicircle, and the boundaries or the boundary points here is actually the bottom semicircle. Okay, so here x, you move it from -3 to 3. Then your y is actually part of the equation of the circle. So here is y equals to minus 9 minus s squared. Please correct me if it's wrong. And this is the positive part, which is y equals to square root 9 minus s squared. Okay, so let me just move this a bit. So this is z equals to 0. So here y equals to this one, minus 9 minus x squared, and this is 9 minus s squared. Okay, so please try to do this yourself. I mean, after this class, okay. You're supposed to get, I don't know whether this is doable or not. I think it can be solved, and you're supposed to get the same answer as this actually. Yeah? So this is, oh no, okay, dot dot dot, and it's supposed to be 1 to 2 pi over 3, and this is also to solve it until you get 1 to 2 pi over 3. Okay. So what time is it now? It's 3. So we have to bring another few other example. Okay, so let's have a look at this. Example number 2, and then we take a break. Okay, so converting triple integral from rectangular to coordinate cylinder. Okay, sometimes you are given triple integral in Cartesian coordinate, and for some reason it's difficult to solve this integral. So you, in this case, probably one of the solutions is to convert this integral from Cartesian, or rectangular to cylindrical coordinate, and then evaluate it or solve it as usual. Okay, so every x, this is like a substitution that we've seen many times before. Every x in your integral now must be r cos theta. And because you've learned this relationship, and then every y will be r sine theta, and z is maintained. I mean, you don't change anything related to z. Okay, so you have something like this. I mean, you substitute them. Okay, here is a triple integral in Cartesian coordinate or rectangular coordinate. This is integral or triple integral in cylindrical coordinate. Okay, so let's have a look at this. Okay, let's say you are given this. Okay, I think this is quite easy because it's just a polynomial function. It's a linear function. Okay, we can try to solve this integral directly in rectangular coordinate, in Cartesian coordinate. I mean, just integrate with respect to z followed by y and x. You can try it. Okay. But now we are talking about how to solve, I mean, this in cylindrical coordinate, assuming that this cannot be solved using Cartesian or rectangular coordinate. Okay, but I think you can solve this using rectangular, as I said just now. But they assume that we can't solve them directly, so we need to use or convert it to rectangular, sorry, to cylindrical coordinate. Okay, so we need to, in this case, we need to understand this. What is this? Okay, so just take this. Okay, we need to be able to sketch the solid actually in order to understand them. Okay, so let's paste it here. Oh, sorry. Okay, so this is our, this is z, y, and x. So this is our z, this is our y, and this is our x. Okay, so this is z equals to 0, and this is z equals to 9 minus x squared minus y squared. Okay, so you know that this is a paraboloid. Okay, I mean, like, it's like a quadratic function, but it has two components, x and y. So if you draw it, so it's probably something like this, where the maximum point is 9, n, which is, this is the origin. When x equals to 0, y equals 0, then you have z equals to 9. So this is your z, sorry. This is x, this is y. And as x and y increase in value, then the z will decrease because this is negative, this is negative. So when this is increased and this is increased, then 9 minus positive numbers is always becomes smaller and smaller. So that's why the value of z decreases, which actually is true here. Okay, so the when z equals to 0, which means you equate this with 0, then you get x squared plus y squared equals to 9. So it's a circle with radius 3. Okay, so it's like this. I mean, the sketch of this equation. I mean, this z here. And now you have y. Okay, so you can guess. I mean, this is like a circle. Okay, so you have y equals to minus 9 minus x squared, which means that you have x squared plus y squared equal to 9. Then you have the positive part, which is will give you the same equation. So now you have equation, or you have a circle like this. So just sketch them. So hang on. This is x, this is y, and this is 3 minus 3 and minus 3. Okay, so you just sketch them. I mean, you haven't finalize everything. And now your x is from -3 to 3. Oh, okay, so this is quite obvious. Like if you take from here and you move it, oh sorry, to the positive x direction, like this, okay, and then this is bigger, I mean becomes longer and longer, okay. So the equation of this, I mean here, oh sorry, just forgot the ruler, okay. Since it's circle with radius 3, so it's s squared plus y squared, I mean just this equation, okay. But in terms of y is 9 minus s squared square root. This is y equals to minus 9 minus s squared, and then the square root. Okay, so this is actually the full circle. This is your r. And this actually comes from the paraboloid. And this actually comes from the z equals to 0, which is the base, or the base of the solid. Okay, so which means that all these things is actually the paraboloid here, but bounded by the z equals to 0. Okay, so something like this. Okay, these two contribute to this. And these two, I mean this one contribute, this one contribute to the surface here, and this 0 contribute to the base. Okay, so in order to use cylindrical coordinate, we need to rewrite G in terms of the cylindrical coordinate. Okay, so let's write G, which is r theta z, okay, where r and theta comes from the r here, which is here. So you have, let's start from here. You have one complete circle, which means that the theta is from 0 to 2 pi. And for all these, the value of theta, you always have radius from 0 to 3. Okay, so here r from 0 to 3. Okay, so here, sometimes I write r here and theta here, but I think it doesn't matter. And theta or r, you can change their position. Sorry, when writing like this. And then the last one, which is the z component. Okay, so you have here, as I said, the z, you doesn't change it actually. It's the same z. So you start from z equals to 0, which means that here z must be greater than 0, and z must be less or equal to 9 minus s squared minus y squared, which is 9 minus r squared. Okay. Oh, sorry, I just forgot this. Okay. So, and then you have the r, and then you want to integrate it to find the volume. So volume, and I think you want to find the volume. No, not find the volume, but to integrate this. So this is your f. Okay, so then we just erase this. Okay, so you have f of x, y, and z equals to s squared, which means that you can convert them in terms of r, theta, and z, which is equals to r cos theta squared. Okay, now here you can rewrite it. Okay. Okay. So here, I mean, we can, of course, we can write. I mean, this 2 is actually double integral r, I mean, over r, and we have certain z limit. This x squared. We have dz, and this 2 is dA. Okay. So now here is, let's say this is theta, this is r, and then you have here the z. X squared now becomes r squared cos theta squared. And dz, we just maintain it. And dA becomes r dr d theta. Okay, so this is r, which means that r from, so just have a look at it here, from 0 to 3, and theta here from 0 to 2 pi. Okay, so that's why you have this. Okay, you want to integrate with respect to z. There is no z here, so you assume that this is constant. That's why I just put it here. Okay, so we get z, and substitute, we get 9 minus r squared, which is here, minus 0. And so it's nothing. I mean, 0, I mean, you just ignore this 0, you get this. And then we want to integrate with dr, with r, I mean, with respect to r, expand this, and you get something like this. This is a constant. And so just maintain it here, and you get this. Now you need to do the double angle identity, and you get this divided by 2, which is how you get 8 here rather than 4. And then integrate this, cos 2 theta equals to sine 2 theta over 2 plus theta, and you get this. Okay, so this is how you do it. I mean, like, everything you are given in terms of x, y, and z, and you need to integrate them by using spherical coordinate, cylindrical coordinate, in which you need to convert them to r, theta, and z, which is what we do here. Okay, so let's take a break. Right now 3:13, so let's resume at 3:20. Okay, we're gonna continue with example 3, example 4, and the next topic, which is the spherical coordinate. It's actually not much. I mean, it's quite different from the spherical cylindrical coordinate, but we'll see this after this. Okay, so let's resume at 3:20. Okay, thank you. Okay, so let's continue with our topic. Okay, so hang on, this is okay. So okay, so here we are asked to evaluate the triple integral of y over g, where g is a solid, yeah, enclosed by the plane z equals to x plus 2 from above, and then from below by the xy plane, and laterally by the cylinder. There are two cylinders actually. Okay, this and this. Hang on. So what do I do? Yeah. Okay. Let me see. Okay, so this is different from. I mean, this is quite similar to the number one. And okay, so this is different from example one, because example one you are asked to find the volume, in which actually you are not given the f as a function of xyz or r theta z. Okay, and for example 2 you are given the f, which is equals to x squared. Okay, so for example 3, I mean example 3 is quite similar to, I mean it's similar to example 2 in terms of the presence of the f. So now from here, I mean from this, let's take them. Okay, next page. Okay, here. Okay, so this is your f of x, y, and z. Okay, sorry, which means that we can convert it to, I mean, by using this, which means that x, y, z will no longer be in the integrand because they are replaced by r, theta, and z. Okay, so but it's not, I mean, it's not difficult because the y, I mean, the integrand here y is actually just I mean r sine theta, which is f r theta z. There's no z here, but there's no issue here. So dv here, so let's see here. Hang on. So let me see. Okay, here. Okay, so let's try to, I mean, sketch this. Okay, because there are four things here. Okay, so you have here cylinder, two cylinders which actually bound this solid G. Okay, so I mean in the xy plane. Oh, sorry. Okay, I mean I'll just draw it here, and this is the x, and this is the y axis. Okay, so let's take this. So you have here x squared plus y squared equals to 1, which is a circle centered at the origin with radius 1. Okay, so just let's draw this. I'm sorry if it's not really good sketch. Something like this. Okay, so this is 1, this is 1, this is minus 1, and this is minus 1. Okay, we know that this is x squared plus y squared equals to 1. And then we have another one. Okay, x squared plus y squared equals to 4. So it's obvious that this is a circle centered at origin with radius 2. And because we have 4, I mean, sorry, because it's here equals to 4, which means this is 2 squared. This is 1, which is 1 squared. Okay, so let's take this one. Let me just create the mark here and connect them. I'm sorry, it's not really good. Okay, something like this. Okay, so this is 2, this is 2, this is 2, and this is, no, this is -2, and this is -2. Okay, so from the top, I mean, the view from the top is actually something like this. Okay, so this is circle, which is 2D thing or 2D object. But now in 3D it's a cylinder. Okay, so in 3D, I mean, let's just sketch this quickly. Okay, something like this, and you have probably like this one, and this is 2, and then because cylinder is unbounded, okay, so you can have, oh sorry, I forget to use different color, I don't know. Okay, something like this, and there is another one here, and oh sorry, and here. Okay, which means actually you are only going to consider this region only. I mean the region that is located between the two cylinder. Okay, which means, I mean, if you look from the top, you'll see something like this. I mean, it's like a donut. Okay, but now you'll take this. I mean, you consider this. Everything in between these two cylinder. Okay, then of course you can. You can draw. Oh, sorry. Okay, something like this. Okay, and then probably something like this. I don't know. Okay, and then you want to consider only everything in between. Oh, sorry. Okay, which is here, which is here, and here. Okay. Okay. Of course, you will. I mean, if you want to sketch the whole solid that is counted in this integration, so this must also be colored as yellow. Okay, but the idea is that you're gonna take what's in between these two cylinders, and then now settle with this, and then bounded from below by the XY plane. Now you are lucky, because actually you will only consider up until, I mean, you will consider from this. So this will be your base, and all these things will be ignored. You will not consider them because you start from here going up. Okay, so this is my plane, and then you have another one, a plane z equals to x plus 2. Okay, here plane z equals to x plus 2. Okay, so I'm sorry because I forgot to write. This is x, this is y, this is z. Okay, so now you have z equals to x plus 2. Okay, so this is the positive x direction, this is positive z direction, this is positive y direction. Okay, so if you consider, let's assume that this is z. Okay. Oh, sorry, just forgot the ruler. As always, this is x. Since you have z equals to x plus 2, the gradient is 1, the y-intercept is 2. So you have something like this. So this is 2, this is minus 2. So the gradient is 1, and the y-intercept is 2. Sorry, the z-intercept is 2, which means that you will have a plane. So, I mean, it's hard, to draw. Something like this. Okay, so this is a positive x direction. So this must be negative. So you will have something like this, or probably, no, because this is 2 minus 2. Okay, which means that you must start from minus 2. So I need to write it here. This 2, this is minus 2, this is 2, and this is minus 2. So you must start from here, minus 2, up to here. Okay, or probably you can make it slightly higher than that. Have something like this. This is just one line. You don't want a line because you want a plane. So there will be multiple lines from here to, to here. Okay, so drawing more lines here. Okay. Okay, we have something like this. Of course, we can continue this. Okay, because y doesn't influence or doesn't affect the plane. Okay, so so if you see, if you are from, let's say, if you are from here, let's say this is your eyes. Let's see, if you are, is a parallel with this, then this is what you are going to see. Okay, so from here, I just forgot. Okay, and then we haven't finished yet. Okay, so this is actually the plane. Okay, and then the plane will intercept with the another wall of the cylinder, which is at s equals to 2. So I need to use a ruler here. So this is 2. Okay, and then you have this, hang on, yep. And then because this is, this is a cylinder with hole in here. Okay, so you have, this is 1, this is minus 1. Okay, so minus 1, and this is 1. Okay, which means that this and this, if you see from here, you'll see something like this. And actually, this is also colored yellow, which comes from the part here. Okay, but you can imagine that this is the cross section, okay, of the solid G. Okay, you have this part, this part, and this part. Okay, So this is from here, and this is from the top. Okay, it's a torus, I mean a donut. Okay, this is from the cross section. Okay, and this is from, I mean, from I don't know what angle is this. I mean, this is something like this. Okay, I mean it's quite hard to draw it. I mean it's 3D, but I hope you can imagine. I mean, like always when you have this kind of thing, you draw. I mean, try to reduce it into x and y plane, x and z plane, or y and z plane, and so on. Okay, so you have something like this. Okay, so is a I mean, from the top is a it looks like this, a donut, but it's actually the roof, the cover is not straight, but it's actually an inclined plane, which is something like this. Okay, I'm sorry because it takes quite long to describe this. Okay, but we still have like 20 minutes. Okay, so yeah, okay, so let's write the G. Okay, the how we describe it. So our G, which is R, theta, and Z. Okay? So R is the radius, right? Okay, so I mean this R and theta is actually what describe our R, which is this. Okay, so of course, I mean, like we start from, I mean, we have a line here, okay, and then we move, or we just move it in this direction, okay, which means that we are going to move this from theta 0 until theta equals to 2 pi. Okay, so here theta from 0 to 2 pi. Then r. As we move theta from 0 to 2 pi, our r always here and here. I mean, regardless of what the angle is. Okay. Okay. Regardless of the angle, here as I draw here. Okay. Our r, I mean, distance from the point to the origin always constant. I mean, like here is always 1, and the outer boundary here always 2. Okay, so here r is from 1, and not from 0. Okay, allows if r from 0 to 2, then you have a full circle, but now it's not full circle, it's a torus. No, it's not a torus, it's an annulus. I'm sorry, I'm quite sometimes I use so it's a torus is 3D. I mean, it's a donut in 3D is called torus, but in 2D is annulus. So what I meant here is actually an annulus. Okay, 2D. I mean, it's donut in 2 dimension. Donut in 2 dimension is a torus. Yeah? I'm sorry. I mean, if I said torus just now, just change it to annulus. I mean, the idea, but it's still the same thing. I mean, like what I meant here is that it's something like this. Okay, so you have this. Okay, looking good. And this is R, and you need another one, which is Z. Okay, as you can see here, this is your Z. So the bottom part is actually 0. At the top part here, the roof is this equation, which is x plus 2. But what is x? So go back to our definition. So x is r cos theta. Okay, so Z is, just use this. X is r cos theta plus 2. And then tutup, close it. Okay, now good. These are constant, only this function. Now what you need to do is to find, hang on, to find the, oh, sorry, not this one. Yeah, here. To integrate it. Okay? Here. So just take them on screen. and put them here. Okay, so we have this. Okay, so let's decompose it. Okay, so you have z limit, this is y, and this is your dz, and this is your dA. Okay, and now change everything to cylindrical coordinate. So this is theta from 0 to 2 pi, and this is r from 1 to 2. Okay, so I mean, just remove, I mean, you can remove this, and z from 0 to r cos theta plus 2. And this is y. So we know y is r, no, r sin theta. Dz, we don't change anything. dA is r dr theta. So I just write it here, and I put r here. Okay, so let's rewrite it just to make it a bit tidy. Okay, so not really tidy actually. So this is r squared. Okay, and then you solve. Okay, so something like this. I mean, the answer is already here. I mean, the solution, not the answer, not only the answer. Answer is this, 0. But the solution, I mean, the working is here. Okay, so let's see, I mean, let's see how this is actually done. So integrate with respect to z, there's no z, so everything here becomes constant. But now you have this, the complicated limit, which is something like this. Okay, and then integrate with respect to r. Okay, so this r is just polynomial function. Here and here, you get until here. Oh, okay, this is good. Integrate with respect to theta, so sine theta become minus cos theta, is here. And then sine theta cos theta, you get sine theta squared or cos theta squared. It's up to you. Okay, so you get something like this, and finally you get equals to 0. Okay, so this integration is not difficult, but how you reach this, I mean, how you convert the g from I mean from this, eh? I mean, Cartesian or rectangular to cylindrical coordinate. I mean, it's quite complex actually. Okay, so please try the. I mean, if you don't really understand, I mean, you can ask me, of course, but you can I mean, take more time to understand this. Okay, so example 4. Okay, now it's specifically asking to convert the iterated integral. I mean, the iterated triple integral like this to iterated integral in cylindrical. No, not cylindrical cylinder, but cylindrical coordinate. I will correct this after this, and then evaluate the integral. Okay, so how do you do this? Okay, here, I mean, okay, this is z equals to x squared y squared, which is like a ball. I mean, it's a paraboloid, but with I mean with I mean concave kind of ball. Okay, and then this is a cone. This is a cone. Okay, and then here, so I mean, yeah, we have like 15 minutes. Okay, so let's just take this. Okay, example 4. Okay, I always forgot to write the number of questions that we do. Okay, so this is easy. I mean, this is our f of x, y, and z. We can change it to f r theta z anytime, because we know the function for the substitution. Okay, so this is our dv, which is equal to dz dA, which will be r dz dr d theta. Okay, so this is fine, this is fine. Okay, so this is z equals to x squared plus y squared, which is z equals to r squared. Okay, and this is actually z equals to square root of r squared, which is r. Okay, and then here, this one is quite easy because you can directly change the x squared by y squared equals to r squared. Okay, but it's different from example 3 because you were not given this kind of thing, and you just given the surfaces that form this G, and you need to determine them in terms of the cylindrical coordinate. But this is different. This is a bit easy here. For here, because you can clearly see that this is r squared, this is r. Okay, but now how about here? Okay, so let's go back to this. Okay, so this is the x, so this is your x, and this is your x, of course. This is the y, this is y, then you have y here and y here. Okay, so usually when we discuss about the spherical coordinates, spherical coordinate after this, they are all usually related to a circle, in one way or another. Okay, so let's draw our xy plane. Okay, so this is our x, this is our y, and we are interested with y from -1 to 1. Okay, this one. But here our x start from 0, which means that we only interested in this part. Okay, where x, hang on, we see, okay, greater than or equals to 0. Yeah, we don't really care what happened in the other side. Okay, so we have x equals to 0, and then s equals to 1 minus, square root of 1 minus y squared. So s equals to square root of 1 minus y squared implies that is actually part of a circle with radius 1 centered at 0. Okay, so of course we can draw something like this. This will be 1, and something like this. Oh, sorry. And just extend this to here. This is -1, this 1, 1. Okay, but we don't care about this part. We just care about the other part. The right portion of this circle. Okay, so now this is true. This is x equals to 1 minus y squared. Okay. Okay. So here, so I think it's quite obvious, the region here. Okay. So okay. So let's write our G. Okay. So here, we have G, R, theta, and Z, where R, okay, we can start from theta. Theta is from here. We start from here until here, which means theta is from minus pi over 2 until pi over 2. Okay, because it starts from the negative y-axis, which means start from here until here. Okay, so as we move from theta equals to minus pi over 2 until pi over 2, okay, so we have our line here where the end point or the boundary always, I mean, here, I mean, at the origin, and the other one always at the boundary of the circle, which means that now our R is from 0 to 1. Okay? Okay? So this is from polar coordinate, nothing new. And then our Z. Okay, now we don't really sketch it. I mean, the solid, because it's obvious. I mean, here, this is R squared, and this is from R. Okay, done. Okay, so our integrand, hang on. Okay, here, okay, let's rewrite it. Okay, so, oh, hang on, to put it here, because I need more space. Yeah, okay, so this will be our R, which is theta and small r, and this will be our Z. Okay, and this is our F of X, Y, and Z. This is dz. This is dA. Okay, so just use everything here. Okay, so theta from minus pi over 2 until pi over 2. R is from 0 to 1. Z equals to, use this, R squared. R. And then here, X is R cos theta. Y is R sine theta. And Z is still Z. And then we have dz. And then we have dA, which is R dr d theta. Okay, so let's rewrite it just to make it a little bit tidy. Oh, but my handwriting is not really good. So you have here, what is it? R cube, or you have another R here. And then Z, you have sine theta, cos theta, dz, dr, d theta. Okay, just make a bracket here. Okay, so you have something like this. Okay, hopefully it's correct. I mean, it's matched with the answer that I wrote here. R3z sine theta, cos theta, dz dr theta. Sorry, this is supposed to be C, not K. Because in Bahasa Melayu, in Malay language, nation language K. So it's, I'll correct it after this. Okay, so please try to solve this, and you're supposed to get 0. Okay. You can try to solve this directly. I mean, without converting to cylindrical coordinate, and try to solve it. I mean, I don't know whether it's doable or not. I think probably yes. Okay, and then you're supposed to get 0 as your answer. Okay, and then probably another one. I mean, just a few minutes because it's almost 4. Okay, say that G is the solid bounded from below by the cone. Okay, this is cone. Okay, Z equals to square root of x squared plus y squared, and from above, sorry, this is from below by the cone, and from above by the paraboloid. Okay, something like this. And then write a triple integral. I mean, write a triple integral to find the volume of G in the first octant. Okay, so there are a few information here. Okay, so this is a cone. When we learn about cylindrical coordinate tomorrow, okay, then I think we will get a clearer picture of why this is called a cone. Okay, and this is a paraboloid. We've seen this many times. Okay, we want to find the volume of G. Now we don't have the F, where F is function of 3 variables. And the first octant, okay? So, I mean, you've seen before, you can have in 2D, you can have first quadrant. First quadrant is when X greater than or equals to 0, Y equals M greater than 0, which means that If this is your X, this is your Y, then it's actually this part. But in 3D, you might encounter many times first octane. Okay, first octane, because now your region is divided into 8 sub-region. Okay, so the first octane is X greater than or equals 0, Y greater than or equals to 0, Z equals to greater than, greater equals to or greater than 0. Okay. Okay, so here you have a cone. So let's after. Okay, so let's draw this a bit. Okay, so let's say this is your X, this is your Y, this is your Z. Okay, and it says that solid G bounded from below by the cone here. Okay? So it's cylindrical cone. So I use this different color. Oh, sorry. Hang on. Yeah. Something like this. So, I mean, this is actually unbounded. I mean, it can go to positive infinity value of Z. Okay, you have something like this. Okay, and then you have the paraboloid. Okay, I mean, here you can see that you have the code Z equals to square root of x squared plus y squared. When x and y equals to 0, you have Z equals to 0. And that's why you have this point. Okay, as x and y increase in value, then Z also will increase. Okay, because it's just I mean, it has direct relationship here. This is always positive, this is always positive, so this is always, I mean, positive, and it will increase as x and y increase. And now the second one is the paraboloid. Okay, which is Z equals to 2 minus x squared minus y squared. Okay, so it's like in quadratic, I mean, something like this. Let's say this is your let's say this is your x, this is your y, for example. I mean, you've seen this before. Okay, so it's like use different color, probably something like this. Oh, sorry. Hang on, how do I do this? Oh, oops. Okay, and then there's a something like okay, I guess something like this, and then this must be 2, because when x and y equals to 0, then z equals to 2. As you increase the value of x and y, so this is positive, then z will decrease. That's why the height decreases until you reach certain extent, z intersect, I mean the surface intersect the xy plane, which is actually just equate with 0, and you get x squared plus y squared equals to 2, which is square root of 2 squared. So it's a circle with radius square root of 2. Okay, something like this. And then it says that the solid G is bounded from above by the cone and bounded below by the cone, bounded from above by the paraboloid, which means that you just consider this. Okay. Of course, you have your intersection. Yeah. Oh, sorry. Okay, it's like ice cream, right? So you have the sharp the cone here, and then you have like I don't know, kind of hemisphere kind of thing at the bottom, actually at the top. Okay, so you need to find. You don't really, I mean, your domain of integration is actually the projection of this intersection here, and this is your R, not the green one. Okay, so you need to find an intersection, which is just equate them. So you have Z, which is square root of x squared plus y squared, and then the second function is 2 minus x squared minus y squared, and you're supposed to get a circle with certain radius. Okay, so you have actually, I think it equal to 1. Okay, so please try to solve this, and you're supposed to get this. Okay, I'm sorry. Now we are 2 minutes exceeding the time. But thank you very much. If you have any question, you can ask. I mean, this is online, so it doesn't matter. We don't need to leave the class. Okay, so if you have anything, just leave. Okay, thank you.
Thank you.
Thank you, doctor.
Okay.
Thank you, doctor.
Thank you, doctor.
Thank you, doctor.
Thank you so much,
I'll
doctor.
see you tomorrow.
Thank
you, doctor.
Thank you, doctor.
Mm.